Now a quick disclaimer, I cannot guarantee that everything said in this video is 100% accurate. I'm no expert in this field. But there's been a recent news about something related to Faraday effect, so I thought I'd make a video on that. Enjoy!
So, have you ever wondered how you actually build a quantum computer? I mean, not just the theory, but the real physical nuts and bolts of it all? Well, in this explainer, that's exactly what we're going to do. We're going to build one step by step, at least conceptually, using pretty much just two things: trapped electrons and beams of light. Okay, let's kick things off with a pretty wild question. What if you could actually compute with a single electron? Now, this isn't just some sci-fi thought experiment. This is the absolute core idea behind quantum computing. And it's the key to that promise of an exponential speedup. You know, the power to solve problems that are just completely impossible for even the most massive supercomputers we have today. So, where do you even begin if you want to compute with a single electron? Well, we've got to start with the absolute heart of it all, the engine of quantum power. And that brings us to part one, the qubit. All right, so first things first, let's define our terms here. What exactly is a qubit? Well, a qubit, that's short for quantum bit, is the fundamental unit of quantum information. And this is where the magic really happens. Thanks to the strange rules of quantum mechanics, a qubit can be in what's called a superposition. That means it can be a 0 and a 1 at the exact same time. Wild, right? And this is where you can really see the difference. Think about a classical bit, the foundation of every computer, phone, and tablet we use today. It's basically a light switch. It's either on or it's off, a 0 or a 1, that's it. But a qubit is more like a dimmer switch. It can be fully on, fully off, and a whole range of possibilities in between, all at the same time. And that ability to hold so much more information is exactly where that incredible quantum power comes from. Okay, so this qubit idea is cool, but it's still pretty abstract. To make it real, we need an actual physical thing to be our qubit. For the technology we're looking at, our qubit is a natural property of a single electron called spin. Now, don't get too hung up on the name. You can just think of it as the electron's own tiny internal magnet, its magnetic orientation. And we figured out how to trap that single electron inside a semiconductor. All right, great. So we've got our qubit, the spin of a single electron. But, an electron is ridiculously tiny, and it's not exactly easy to pin down. We need some way to hold it perfectly still so we can work with it. And that brings us to part two, the quantum dot. Think of it as the perfect tiny trap for our electron. So what is a quantum dot? Well, it's this tiny little island made of semiconductor material. And when I say tiny, I mean it's on a nanometer scale. It's so small that it actually starts to act like an artificial atom. Its unique structure creates this kind of energy well that's just the right size to trap and hold one and only one electron. It perfectly isolates it for us so we can finally start working with it. And you know what's cool? Building one, at least in principle, is surprisingly straightforward. It's kind of like a recipe. First, you start with a flat base of a semiconductor. We call that a substrate. Then you grow a tiny little island of a different semiconductor material right on top of it. A common combination is indium arsenide on top of gallium arsenide. Because the two materials don't line up perfectly, that mismatch naturally creates a stable little trap. It's the perfect home for our single electron qubit. Okay, let's do a quick recap. We have our qubit, an electron, and we have its home, the quantum dot that's trapping it securely. So, what's next? The obvious question is, how do we actually talk to it? How do we send it instructions? Well, the answer is pretty elegant. We use light. Specifically, we use photons.
Now, to control that electron's spin using light, we need a little help. We need a special middleman, let's call it, known as a Trion state. Here's how it works. When we zap our trapped electron with a photon from a laser, we briefly kick it into a higher energy state. For a split second, this creates a temporary little system made of two electrons and one hole. And a hole is really just what it sounds like, the empty spot an electron used to be in. This fleeting, unstable Trion state is the absolute key that lets a particle of light talk to and control the electron's spin.
And this process is just incredible. So, step one, we fire an ultra-fast laser pulse tuned to the perfect frequency, and it smacks right into the electron. Step two, bang. That instantly creates our temporary Trion state. But this thing is super unstable. So step three, in just a few picoseconds, we're talking trillionths of a second here, that Trion state collapses. And as it collapses, it flips the electron's spin. And just like that, we've done it. We've performed a quantum operation. So, this all sounds pretty amazing, doesn't it? It seems like we've got it all figured out. But there's a villain in our story. There's this huge fundamental challenge that every single quantum computer, no matter how it's built, has to face. And that brings us to the race. The race against something called decoherence. Decoherence is, without a doubt, the arch nemesis of quantum computing. That special superposition state our qubit is in, it's unbelievably fragile. The best way to think about it is like a perfect, delicate soap bubble. Any little thing from the outside world, a tiny vibration, a stray bit of heat, a magnetic fluctuation can come along, touch that bubble, and pop. The qubit just collapses into a boring old 0 or 1, and all that amazing quantum information it was holding is just gone. Forever.
So what's causing all this trouble? What's popping our quantum soap bubble? Well, for the system we're building, the main culprit has a fancy name, the Hyperfine interaction. But what it really means is this. Our little electron qubit is sitting in a semiconductor, and it's surrounded by thousands of atomic nuclei. Think of them as noisy neighbors. Each one of those nuclei has its own little magnetic field, and altogether, they create this constant, chaotic magnetic noise that's always shaking and jostling our qubit, eventually causing it to decohere.
And this really puts the challenge into perspective. Look at these timescales. It's a race against the clock, and the clock is insanely fast. Performing one of our quantum gate operations, flipping a spin with our laser, that takes about 10 picoseconds. But the decoherence time, the amount of time we have before the environment destroys everything, is only about 1 to 10 microseconds. So we have this tiny fleeting window of opportunity to get our entire calculation done before the quantum state just vanishes.
Okay, so let's put all these pieces together now. What's the end goal of all this? We took a qubit, the electron spin, we trapped it in a quantum dot, and we figured out how to control it using light. Well, these controlled qubits are the fundamental building blocks. We use them to create what are called quantum gates. And quantum gates are basically the same for a quantum computer as logic gates are for a regular computer. They're the basic operations you need to run an algorithm. And here's where it gets really mind-blowing, the potential for scale. Because these quantum dots are so incredibly tiny, you can pack them together super densely. I mean, the research suggests that with this kind of technology, you could theoretically fit 100 million qubits on a single chip, just 10 by 10 centimeters. That's just an incredible density. But why does packing in so many qubits matter so much? Well, this quote really hits the nail on the head. It says that adding just one more functioning qubit can literally double the power of a quantum computer. That's the equivalent of 18 months of progress under Moore's law for classical computers. It's because the power grows exponentially. You're not just adding power with each new qubit, you are multiplying it. That's the game changer.
So there you have it. We've walked through how to trap a single particle, how to talk to it and control it with a focused beam of light, and how to perform a computation in the tiny window before it has a chance to forget. It's an incredible process, and it all leads us to one final, fascinating question. Could it be that the future of computing, the very machines that will one day solve the world's biggest and most complex problems, will be built with nothing more than trapped atoms and focused beams of light? Let's talk about something that holds back even the smartest people from really succeeding in fields like engineering, physics, you name it. It's not about how smart you are, and it's not about passion. It's a single, fundamental roadblock that most people just don't see coming. So why is that? Why does someone who can grasp these incredible, complex theories in electronics or advanced mechanics suddenly hit a wall? What is this invisible barrier that just stops so many talented people right in their tracks? Well, this quote from a veteran engineer just hits the nail on the head. All of that incredibly advanced, mind-bending stuff, it's all built on the algebra you learned in high school. But here's the catch, and it's a big one. You can't just kind of know it. You have to really know it, inside and out. And that brings us to the main point here. The foundation isn't just important, it's everything. It's the bedrock that every single advanced skill is built upon. Let's break down why this is so unbelievably critical. Okay, so before you can even think about manipulating something like derivatives in calculus, you have to be an absolute wizard at shuffling equations around. And that's pure algebra, right? Or what about mastering imaginary units for electrical engineering? They're not just some weird abstract idea, they're a vital tool. And using them, yep, that depends entirely on how solid your algebra is. And then you've got vectors and polynomials in physics. That's the language of the field.
Trying to work with them without a fluent command of algebra it's like trying to write a masterpiece novel when you don't even know the alphabet. So the bottom line is this. You need an absolutely unshakable foundation. When you're wrestling with some big, hairy, complex problem, the very last thing you want to be worried about is whether you made a simple algebra mistake. That right there, that is the hurdle.
So if a shaky foundation is the real problem, what's the solution? Well, this is where a tool built specifically for this comes in. And today, we're going to look at one called Algebra because it's designed to fix this exact problem.
So what is Algebra exactly? Think of it as a super comprehensive, high-end video series that's all about one thing, building your algebra foundation from the ground up so it's rock solid. It's not just a review, it's a complete rebuild.
But here's the thing, Algebra isn't just a bunch of videos. It's a whole structured system, a method designed to get you to true mastery. Let's take a look at how the Algebra method actually works.
The Algebra method really rests on these 4 pillars. First, it's guided learning. It's a journey where every single step logically builds on the last. Second, it's all about practical relevance, so you actually see how this stuff shapes the real world. Third, the explanations are amazing. They just break everything down into simple, digestible steps. And finally, you can track your progress with these cool interactive checkpoints, which really helps you stay on track. And like I said, this isn't just about watching videos. Algebra gives you a complete toolkit, everything you need to actually succeed. So what's in the box? With Algebra, you get interactive problem sets and quizzes to really sharpen your skills. You get downloadable reference materials, you get access to a community for support, and you get unlimited access to all 150 episodes. And you can watch them anywhere, on your phone, on your desktop, wherever. But on top of all those features, the people behind Algebra do something that really shows how much they believe in their program. It comes down to this number, 60. It's a 60-day, no questions asked money-back guarantee. I mean, that means there is literally zero risk for you. You can try Algebra, go through everything, and if it's not what you need, you get a full refund. It's really that simple. Okay, so if you're feeling like, yeah, this is me, my foundation needs work, Algebra has a few different ways you can get started. Let's look at the learning paths you can choose. You've got a few options here. The weekly plan is awesome if you just want to dip your toes in and see what Algebra is all about. If you're ready to commit a bit more, the intro or intermediate packs are great. And for those who are all in on total mastery, the full series gives you everything. It's really just about what works for your goals and, your budget. Look, the advanced stuff is the fun part. I get it. But it's mastering the fundamentals that really unlocks your potential. So please, don't let this one single hurdle hold you back from the future you want. You can fix this. The first step is super easy. Just head over to algeprime.com to check it out for yourself. That's ALGEPRIME.com. See if Algebra is the tool you need to finally build that foundation for good.
Thanks for watching to the end of this video. If you want more content like this, there is a playlist that should be popping up right now. Stay tuned for more. I've also made this free video for you with solutions for creativity, financial strength, and online security. I hope you'll enjoy this offer as well as all the others featured on my channel. And that concludes this video. Thanks for watching, and until next time, this is Hermolau Tube. My name is Konstantin, reminding you that your interest is the current that powers this channel.